So our next speaker is Wolfram Ratzinger, and he's going to talk about towards coordinate-independent estimates for electromagnetic gravitation wave detectors.
Okay. Yes, so this works. Okay, very good. And then this I use to move forward. Okay, very good, very good. Okay, yes, thanks for having me. So we already had a lot of interesting discussions on this topic, because essentially what the talk is about, it's this kind of detector. You have some background electric field configuration, you have a gravity wave coming in, and you want to reliably predict what kind of change the gravity wave produces in your detector, and you want to then pick this up. So we've seen it with abracadabra, the cavity in a constant background magnetic field. So we've seen a lot of incarnations of this. And if you take a principled approach to describing such a detector, you maybe want to follow this list I've outlined here. So you want to understand all the components of the detector in full GR. Then you want to go to the special case where your metric is the Minkowski metric with small perturbations. So you need a perturbation theory for this. And an important point is that because GR is supposed to be a geometric theory, so it cannot depend on the coordinates you choose to describe the space-time, the perturbed theory should inherit what we call gauge invariance. And in maybe at this point somewhat outdated literature, you can find statements that one needs to calculate in a specific gauge. So this is of course intention, but I think this has now there's now agreement beyond everyone that this is always linked to further approximation one makes. We've heard things like we assumed the detector is fully rigid, or it's free falling. You remember one of the slides that Sebastian showed on Monday that exactly went into this. But nevertheless, this road is still a bit unclear, as has become as we have seen from the discussions we had. So I want to tell you what we think about this. So starting with the full equations, without any assumptions about the metric perturbations being small, I think there's not much debate that these are the full Maxwell equations. So you get these from kind of, I think, what is called the canonical. So you take the Maxwell equations in the flat space-time. You have your action, and if you promote all the metrics that show up in there to the curved metrics, you get these Maxwell equations. But what is maybe not so much discussed in the literature is what are the observed fields. And this goes a bit, in yesterday's discussion we had Diego say we need to come more to an apples-to-apples comparison. So clicks in a detector. And, oh, shit. So I still want to talk about this. So we need to specify what is really the field. An observer here travels along its world line through the curved space-time manifold, and you want to say what does this observer measure, what electric and magnetic field. And the key point to realize is that this f we have here now is now a tensor that transforms under coordinate transformations. So it's not the thing we had in special relativity, where this was just a combination of the E and B fields that a stationary observer would see. So now the extra step we have to do to get to an observed field is to contract this tensor with a tetrad. So the tetrad can be thought of as an infinitesimal coordinate system that this observer carries. So of course it has 3 spatial components. So this is like, how do I point my sensor? So this is like this part here, the EI. So the underscored indices here are not coordinate indices, it's important to note, but those are just numbering. So I want 3 spatial ones, and then I want 1 temporal ones. One temporal one that tells me if the observer is moving or not. Okay, and you can check, no, because here all the space-time indices, so the not underlined indices, they are contracted. So this EI and BI that I have defined, they are coordinate invariant, which is already a great start for an observable. And the same kind of goes for boundary conditions that I think haven't been discussed much in the literature. So you also want to make those coordinate invariant. So we remember from the electromagnetic class, for example, on the conductor, the electric field parallel to the surface of the conductor should vanish on a perfect conductor. And how do you express that covariantly, so independent of coordinates? So we think the way to do is the following, and we also found this very old reference here. The way to do is to consider an observer that is attached to the surface and has the same for velocity, therefore, as the surface. And then you choose its tetrad, so the way the field is measured, such that the 1 and 2 components are aligned with the surface. No? So if this was the conductor here, then the 1 and the 2 direction of this observer are aligned with the surface. So I think this is a covariant way of saying that the field parallel to the surface should be 0. And then now this perturbation schemes, this is still a big topic, as we've seen from the discussion. So let me be brief on that. But essentially, when you perturb the equations that I've shown before, you found these effective currents that we've seen a lot. But also now, when you perturb the boundary conditions, you get a whole host of terms that are usually neglected. So there are, just because your surface, if it's not the old flat surface from before, you have all kinds of effects that are associated with inhomogeneities, or the surface getting tilted, or if the surface is moving, then you see a background magnetic field boosted in the frame of the wall. Okay, and you want to take all of this into account. So, but essentially you want to go back now, have approximations where you can do this again. And the way to do this is to consider frames where the motion is very small. And I mean, essentially, Sebastian already explained this. But as long as the gravity wave frequency times the length is much larger than the sound velocity of all the materials that make up the detector, so essentially the metal, the conductors, we can treat it as free falling. So this means the motion in the TT gauge is suppressed, so with respect to an order of magnitude estimate. And then in the opposite limit, the detector becomes at rest in the proper detector frame. And there's an additional limit that has nothing to do with all of this, with the mechanics. But in the proper detector frame, you can also go to this, what is called a long wavelength limit, where you just drop terms in the metric that are suppressed. Okay, so with this, let's look at some, start with a toy detector. So this is just a toy example from Sebastian and Diego's paper and so on. So you have a homogeneous background magnetic field, and parallel to the field you have a gravity wave incoming. And they already discuss in their paper very nicely that it makes a difference whether or not you observe an electric field depending on if your observer is at rest in the proper detector frame or in the TT gauge. And the only modification we would like to make to that is to not decide this by hand, but to put a physical thing, a rod, so just a stick, and put the observer on the end. And then you can see here, so here in this plot, I'm showing the frequency multiplied with the length of this rod, and on the y-axis I have the magnitude of the oscillating magnetic field that you observe. And so in black you see a full solution that takes in the motion and all the coupling I've showed in the last slide completely, and then I've shown the approximations. So the way to read this is, for example, in the free falling limit we know there's no signal, and you can see that here, so it's 0, but you still get an error. And this arrow does not know about these mechanical resonances here, but you see that kind of like if you throw a dart at the x-axis and you don't happen to hit the resonance, then the arrow kind of gives you the correct order of magnitude. Okay, so this kind of scheme seems to work. Now for the big conclusion of this project, we want to calculate a cavity. In this case, it's a spherical one in a constant magnetic field. And we want to calculate the magnetic field one sees in a very small pickup loop up there. And okay, so this is still ongoing work and we still have problems, but we have some intermediate results that look promising. So here you see the region where you have over here the mechanical resonances, and then you have the electric resonances, and you see so over this range of parameters, you see the free floating and long wavelength limit applying as you would expect. But then when we go to very small frequencies, we still have this offset here, especially also with the rigid limit. So there still seems to be a problem with our formulation, and we are trying to find this bug. So okay, also comparing to other literature, the only other result that has considered the motion of such a detector together with the electromagnetic properties are the results for Margo, as far as we know. And there we also see kind of what we think is a free-falling limit. And as the authors of this paper mention, the rigid limit here severely underestimates the signal you get. So, and of course, this would be very helpful, just to get these two power laws reliably for more complicated experiments like abracadabra and so on. So this is the plan, yes. So thank you. That's all I wanted to say.
Okay, and now we have time for questions. Yes, Camilo.
Yeah.
Thank you for a very interesting talk.
Yeah.
So I have two questions. So if I understood correctly, you are not really relying on this effective current description, but you are just trying to do something more coordinate invariant. Is that correct?
The effective current is hidden in our perturbation scheme.
Yeah, I know,
Okay.
of course.
So,
but you are not really using that to calculate.
No, we also have this like, here, the main signal, the electromagnetic signal here comes primarily from the effective current that rings up the modes. But the point is here, the question is always, or like it was a question in the literature, which effective current to use, the one at TT gauge or the one in the proper detector frame, no? And now if we know that, or in the future, once we have convinced ourselves that this formalism holds, the idea would be to choose the gauge where the detector doesn't move. So here at high frequencies, the TT gauge, no? And then you use the effective current in that gauge to describe it, no? And then in another frame, so if you would do the same, so the claim is that you can get the black line in any gauge. But if you do this in the proper detector frame, you would have the contributions from the effective current and the motion, the apparent motion, they would conspire to give you the same result.
Yeah,
this is kind of what I'm saying.
But then it brings me to the second question.
Yeah.
So if I understand correctly, you took into account the boundary conditions associated with the electric field, right? This is what you did with the
cavity, yes.
But what about the boundary conditions associated with the magnetic field? Because I think, to the best of my knowledge, this is how you recover this thing of like the equivalence between these two frames, in the sense that when you have this magnetic field, the boundaries of the magnetic field also matter, because in there you have these surface currents, and then they when you account for the different gauges, then you get the effects that also conspire to give you the right answer in both cases.
For the magnetic field, you would have something like the component orthogonal to the surface should be constant in time. But I think those are related via the Maxwell equations, no? So I think you can show that because like the change in the magnetic field is related to the rotation of the electric field, no? So if the electric field in the plane is zero, then also the rotation component orthogonal to it is zero. So therefore, I think the Maxwell equations kind of imply this then. But yeah, we are also working on formulating it.
I think you also have to account for the boundary condition for the magnetic field over which the conversion is happening.
Yes, but I think at some point you have enough equations to solve. So I think we have enough equations right now to get one solution, no? And then these other things would be additional properties of the solution, kind of. So like, also with the Maxwell equations, you have like 2 times 6 in total or something, but some of them are redundant, no? So the boundary conditions are kind of the same. Some of them are redundant, I believe.
Okay, we can discuss more about this later. But my point is that I think if the boundary conditions are not the same in all gauges, of course, because the boundaries are not the same as you properly mentioned.
Yes, because there's the motion, no?
Yes.
But like the equation I wrote down should hold in all gauges. So it's just that the terms in there are vanishing or not vanishing. Yeah.
Nancy has a question.
Yeah, I have an experimentalist question. So you guys, I wasn't there for Sebastian's talk. So you compare omega L or omega R, which is like the frequency of the gravitational wave times the length of the detector.
Yes.
To me, it would make more sense physically to compare the frequency of the gravitational wave with the mechanical resonances of the detector, because omega times L has no information what the detector is made out of. It could be made out of very high Young's modulus material, different Poisson ratios, which would decide the frequency of the detector. So if I make it out of rubber versus steel, it'd be completely different, whether it's rigid or not.
This is true for the mechanical resonances, no? And you can see here, this is why the mechanical resonances sit here at approximately, in these units, sits approximately at the speed of sound that was chosen to be 10 to the minus 3 here. And then you have the electrical resonances, no, because they move at the speed of light. So in these units, they sit around 1, no? So I think, this was on the previous slide, right? So the electrical resonances, they are at 1 in this scale, but then you're right, the mechanical ones are at small values.
But I mean, it's all in there, right?
Yes.
You have the speed of sound, which consists of all sorts of. Sorry. I mean, you can say.
Okay. I mean, okay. So I think, this is the full thing, no? So the idea is that.
So should I take back from this plot? Like, if I am reading this plot, can I say that if my detector, if omega times R is in this regime, then it doesn't matter what my detector is. I could make it out of squishy, like water or
yes, so
like something really compressible. That wouldn't matter.
This is exactly the blue line. So if it's really compressible, that just means all of this mechanical structure moves further over here.
Yeah. So I cannot use this plot directly, right? So I need to combine the material properties along with this plot. So it might be better to just compare the gravitational wave frequency with the mechanical resonances of the detector. And then we can take, my detector is resonant at 1 kilohertz, and the gravitational wave frequency is 100 kilohertz. So I should be using the rigid regime.
Another thing that we are
something.
trying to establish right now is, you see the mechanical resonances are very important over here, where the first ones sit. But then once you go to the higher ones, you can see their importance dying down, which is reflected in the black line converging to the blue line. So this means every very squishy detector will, if I build the sphere from any very squishy detector, around here, the properties don't matter anymore. It doesn't matter if it's a bit more squishy or a bit less. And this is a nice thing we try to establish for calculating something like abracadabra, where modeling the mechanical properties will be more or less impossible. So we just want to say it's very squishy or it's very rigid, and then we want to reliably calculate. So this is another approach we are taking. But then you are right. Once you have the mechanical modeling, then of course you can choose. So once you know where the resonances are, it's probably better to rescale this. Yeah, I agree.
Okay, so if no more question for Wolfram, I would like to go back to Jan, and Joachim has a question for Jan.
I basically wanted to discuss a little more how the cosmological graviton background could be enhanced in BSM theory. So what can I do and what can I not do to perhaps push this closer to the ineffective bound?
Okay, yeah. So actually, so if you have BSM, additional degrees of freedom, then kind of like the spectrum goes down. It scales with the effective degrees of freedom to the power of minus 11 over 6.
I saw that on your slide. So is there anything I can make to push it up? I don't know, early matter domination, non-standard coupling.
Oh, okay. Yeah, there's a paper by Francesco Muia and collaborators. And
he knows it.
Yeah, he can answer the
No,
question.
sorry, I didn't.
And they have a kination dominated
yes,
phase,
yes.
and then you can enhance it. And
Yes, we can touch the BBN bound, basically.
Yeah,
Cool. So kination domination is the key word.
I mean, it's the only way. Yeah.
Wonderful. Thanks.
So maybe another thing could be if you have extra dimensions and these gravitons are KK gravitons, so then the Planck suppression of operators will not be there. So I don't know if somebody tried to compute this, but in case of if these gravitons are KK gravitons, then might be you might be killing the Planck suppression might begin. Yes, Diego.
Well, can you hear me? Yeah. So the question was related, but also I think it would be useful if we could, given the amount of energy, so try to make a model-independent constraint on how much we can enhance the amount of gravitational waves in phase transitions, in this kind of thermal production. Everything. I guess there should be a limit given by the amount of energy, by the time scales. How much this peak can go up, model independent, you see. I think that could be very useful. Of course, with huge error bars for theoretical, but talking to people who are experts on more than me in primordial universe, for instance, with Danny, he was telling me, no, this is impossible because blah. Okay, so this is the maximum you can get because this is the maximum amount of energy you have, and that's it. Because I was also talking to people doing non-perturbative phase transitions, things which are very hard. And again, they were telling me, no, this is the maximum you can get. In our simulations, you never get this bigger than that. So
let me comment on that.
Yeah, I think it would be very useful for the review in particular if we could estimate some kind of.
So obviously, the largest the more violent the process is, the larger the stochastic background might be. So the typical place where this happens is preheating, and there we have this bound that Dia was mentioning. And it's very simple. You know that you're going to eventually reheat the universe. So you have to ask yourself, what's the fraction of energy, the maximum fraction of energy that I can convert into gravitational waves, given certain energy density, assuming that all that energy density goes into radiation. Because we know what omega in radiation is today, it's 10 to the minus 5. So if you're as efficient as you can, so something like temperature over M Planck, 10 to the minus 6, the largest you can get is 10 to the minus 11 in omega gravitational wave today. So that would give you the peak. Of course, the shape of the spectrum is very different from thermal, at least in preheating. Okay, you have a K cube rise and you have an exponential fall off. But the total integrated energy, which is what affects an effective, of course depends on the spectral shape. So you could have very broad spectra or less, but at least you know the maximum. The maximum, this omega 10 to the minus 11, is dictated by the most efficient way in which you can convert density contrast into gravitational waves, and that's fixed by this ratio. But remember that this temperature that
but that's not universal, right?
This effective temperature doesn't have to be the thermal temperature. You don't need the particles to be in thermal equilibrium. You can still have the effective temperature related to the high occupation numbers. So this would be like K times NK in the low K limit. This behaves like an effective temperature, and this could be as high as 10 to the 17 or so. So there you can increase the effective, but it's not a thermal spectrum. Remember in the Boltzmann distribution that you were having, the collision integral, where you integrate them with frequencies, assuming that they are thermal distributions. They're not thermal distributions. Of course, they are whatever you get from preheating. High occupation numbers at low frequencies.
But I guess my point is
then to the integral.
Taking this into account. So if you have you can have in this section the most pessimistic and the most optimistic scenario for different bandwidth. And if you tell me that, for instance, Francesco has already produced something in this direction, I guess you can estimate, which is the maximum if I am super optimistic. I think that would be very useful for.
In the
I mean,
sorry.
yeah, maybe Andreas. Yes, I think you can always almost saturate the ineffective bound. I mean,
I can say the
you
numbers.
have to squeeze a little bit here and there. Maybe there's an efficiency factor, which maybe is not 1, but something like 0.1 in reality. But I think this is kind of no, because you can have a source which essentially is all of everything. Take a supercooled phase transition where the field that undergoes the phase transition carries 99.99% of the total energy density. Then again you lose. Maybe there you lose a factor 100. Okay, then you're a bit below. But I think this. I wouldn't. I mean, I wouldn't try to. You don't have to over-engineer it, yeah. Or you do kination, as was just mentioned. You produce a small amount of gravitational waves. You have a long period of kination. Then you figure out your reheating, and then you saturate the ineffective bound. And I think that's it.
Yes, Valerie.
I have a question for Anna, if you're still online. And that was that you kind of you computed kind of the spectrum from graviton production from the inflaton decay, and now I was wondering kind of hypothetically, and so I'm kind of asking I think the inverse question of what Fernando was asking earlier, because say hypothetically we measure this, right, and even we measure this with some accuracy, right, in a fantasy world, will we really be able to say something about that gravity is quantized? In the sense that, I mean, the spectrum you got looked actually quite similar to the one that Jan was getting, right? And that, he convinced me, you can go to get in a classical process.
Well, I think that this process can be described classically. So I think that in this case, it's not obligatory to quantize gravitons. It will still be the same. It can be considered like emission of classical wave, produced by 2-point function of. In my case, it's in my case it is 2-point function of some non-equilibrium matter produced during the heating. Otherwise, it could be a 2-point function of plasma, producing the similar graviton, but it would be a 2-point function of thermal equilibrium, and maybe it's easier to compute. Okay. But in my case, just for technical description, it's easier to compute it like a quantum graviton production, because in this case I can compute decay, Bremsstrahlung rate or decay rate. It's easier than compute particle production.
Okay, thank you. That answers it. Yeah.
I believe it's equivalent.
I have one question for Anna. Anna, do you have the slides? So in the spectrum, or do we need to do something?
I can. Yeah, I can share a screen.
We can share here. I think it's easier if we share here. You tell me which slide, and we can share from. If she's uploaded them, we can do here. And we don't have to switch to the Zoom.
So the slide where she has the spectrum. I think if you go to the second last or third last. Yes, maybe this one, yeah. So so in this spectrum, can you hear me? Yes. So in this spectrum, why do you have the IR tail cutoff? Because I would have believed that the IR tail keeps on going, right? In the infrared tail of the spectrum?
Yeah, here I also have infrared cutoff because I will hit the beginning of reheating.
No, but still, I mean, there are no. I mean, you don't have any bounds, right? I mean, the spectrum once you created it, just I mean, in the infrared, there is no reason, I think, to cut it off at some point.
In these plots, it's not yet. It's just not shown. But in fact, there will be bound corresponding to the fact that gravitons were not produced eternally, because at some point there was inflation, and all the production happened during reheating. But there were no production during inflation itself.
Okay, I see.
But this bound is, I think. So I still have to improve this plot with this bound, but it will be quite weak.
Okay, and another thing I was wondering about. So,
yeah.
do you find any difference if the final state during reheating is a fermion or a boson? Because usually in a decay or a scattering, if the final state is a bosonic or a fermion, there is some phase difference or some difference in the amplitude, right? So at the gravitational wave level, do you find any difference?
Not much difference. The only difference that could happen is just enhancement of the number of diagrams, because if you have more particle states, then you just have a factor like, say, if you have 4 degrees of freedom, you have factor 4, because each combination can also couple to graviton. You just have enhancement of number of diagrams.
Okay, any other question? Maybe we can, yes, Valerie.
I have a question. It's a bit of a question to Wolfram's talk, but maybe it's more a question to the audience. And I'm a bit afraid of the discussion I might start with this. But I mean the way Wolfram formalized this with kind of the like making explicit the boundary conditions and making explicit the observer. I mean, to me that looks convincing. So does that? And it kind of does what I more or less expect it would do. So does that answer our questions?
So I think there's still remaining discussion though, because there was a lot like how to write down Maxwell equations and so on. And I think this problem arises when you go from the full equations to the perturbed ones. So I think we have to be aware that when we introduce the perturbation scheme, we make some choices whether or not we perturb co or contravariant vectors. And I think then there's also now a third approach that I think is taken by Francesco and also by what's your name again? I forgot. So there are different ways, different fields that you might consider to be the ones that you split. And then because if you like take F mu nu with indices lowered, then you have this ambiguity that once you perturb this, then on the full side you would raise and lower the indices with the full metric, but in the perturbed system with the Lorentz metric. So there you have to be careful which one, if you perturb F mu nu with the indices lowered or with the indices raised.
If I know how to do it in the full system, right? If I know where to put the powers of the metric in the full theory, then writing the full metric as flat metric plus perturbation and whatever gauge I am, right? I mean, then that should be straightforward, right? I don't see the complication.
But the point is that the perturbed equations we show that they depend on these choices. So the equations might not look the same. And I think for this example where you, with this F menu that I just mentioned, it's been worked out somewhere. I remember reading this. I couldn't remember where. But I had 2 backup slides. You can look at them. But essentially, I think we have to be aware that all the perturbed equations, the look of them will depend on how we choose the scheme. And therefore, it's very important that also how the observables look. So the invariant things, this magnetic field that I showed, this will also look different, and it will account for these differences that are there in between for the not gauge invariant things.
I have one comment on this. So I think, we always have to consider what we are measuring, right? So in the end, you want to measure an E field. And so I think you always do that in the long wavelengths regime. So your antenna is not larger than 1 wavelength, right? So in that case, you kind of get your E fields that you want to measure from F menu. And it doesn't really matter if you have covariant or contravariant, right? Because if you change in the long wavelengths regime between upper and lower indices, and you're in the proper detector frame, it's almost more or less the same, right? So the tensor doesn't really change. So I think that, we shouldn't worry about this too much.
Maybe I can. like yes. So I claimed that the observed. Yeah, maybe we can also just. I think I had it on the slides. But the claim was not that the observed electric field is something like this times up to science. So when you perturb this, all of these quantities become perturbed. And let's say I have a scheme where I go to so I have a background field, and I have a fluctuation. And I do this for all of these quantities. Same. Okay. And you do the same for the tetrad. So now this is, of course, with this choice, this is quite trivial, no? So now my EI just becomes, just put the perturbations on all of these, no? So I have a delta and so on, okay? Let's maybe write one more. So this is now the background. This is a new shit. So, so, and one more term. So now your buddy also does the computation, but he, for example, chooses to start from this. No F menu goes to. I think so. Can you hear me? Okay. Okay, it's good. It's good. Okay. Maybe I just have to be careful here. Okay. So now you have to, if you want to go back to this equation, you have explicit, if I want to write it now with F menu upstairs, this same equation, and I keep this part, now I have explicit insertions of the metric, no? Equal to, and now I need two metrics here. U beta. So I mixed these, I think. Okay. So now you can see there are now two times the metric explicitly shown up, no? And the metric gets perturbed as, I guess this everyone agrees upon. Plus this, no? So now when I write this equation, so my buddy would have a different expression than me with also this h explicitly showing up here. And I think if we take this into account, then we can, because like this part here will be well defined, no? This is like how is the observer attached? Is there torque on this frame here, no? That like rotates the sensor, and does the sensor see any acceleration? So I think we have to be aware that this perturbed equation that I wrote here depends on the scheme I define. So this is, I think, something we have to take into account.
Camilo.
Yeah, so I think this is somewhat related to the question I had before, because in my opinion, the ambiguity appears, and I think we tried to make that explicit in our last paper. The ambiguity, whether you put the indices up and down up here, actually is no longer there if you keep track of what is sourcing, so which currents or which charges are sourcing your external fields. So here, I think, as far as I can see, I think you are not keeping track of that, right? You just assume that there is an external field and that's it. And then I think the point is that also these external fields are sourced by currents themselves. And these currents are also affected, must be affected by the gravitational waves. So I think.
But I would hope, I mean, in my Maxwell equations, when I take the full one, of course, I also perturb the current. No? The current also goes to.
Yeah, exactly. That's my point. Exactly.
Yes.
Once you take exactly. So, but I think that the ambiguity disappears if you do that. So, because I think that was the problem of the approach by, our So they drop the currents fully from their equations, and then just discuss an external field that is homogeneous in
I think
either
for
frame.
the cavity you can do this because, of course, it's assumed that this is a perfect conductor, and you can actually.
I'm not that familiar with the case of the cavity because this is I haven't known. I mean, I have to read your paper when it's out. Okay. But I'm familiar with the case where there is for the case we discussed, the case where there are a toroidal field, and in that case, I think the ambiguity disappears if you just keep track also of what happens to the
coil,
to the current that is sourcing the external magnetic field.
Yes, that should be included, I think.
Yeah.
Yes, Chen.
I have another comment. So I think also kind of like there could be like, I mean, you don't measure the E field, right? You measure, I mean, that's not like something, you measure a current, so you measure it indirectly, so to speak. But I think like there could also be a confusion coming from the fact that, you're not measuring the E field. And when you try to define like a physical E field everywhere, I don't know if it's really so physical, right? You should just think about, okay, I measure like a current, and from this I would infer like an E field. So
I mean ultimately, for experiments like abracadabra that are like half of the experiment is the pickup loop, So there, of course, you want to be very careful to understand how a pickup loop works. And I don't think we are there yet. But for the pickup loop I discussed, I assumed that it's like very small, such that I can say it's fully rigid, and like I made assumptions that are not there for a realistic pickup loop, but in principle it's a limit. So this is okay. I mean,
yes, Nancy.
Yeah, I think I agree with what Jan says, that at the end maybe the calculation just needs to be from the current in the toroid to the current in the pickup loop, and then that's like a fully. You can include everything. And in fact, I was chatting with Valerie yesterday that one thing that's still not included is the relative motion of the magnet and the pickup loop. The magnet is suspended, but the pickup loop is not suspended. So the rigid body approximation is different for your measurement versus for the thing that's creating the magnetic field. So you need to be also careful about the relative motion between those two.
I mean, for the cavity we do, everything is allowed to move. The only thing we still fix is that the pickup loop is very small and therefore fully rigid, And then the current in the pickup loop should just be this fixed size, which is a fixed physical size, which one could get in the proper detector frame of this one observer, So the one of the sensor, really.
But even in your calculation, you have to ask: is the thing that's creating the background field around your loop, is that moving with respect to the loop?
But this we do, like the cavity, everything else is now moving.
Okay.
So this is kind of the point,
Yes, thanks.
Very nice experimentalist question. So all these discussions, I think, to my understanding, it's very important to have a proper calibration of the experiment. But is it also, or is it beyond going calibration that it could also discuss a signal away?
I mean, for the electromagnetic resonances, I think we are apart from symmetry questions. Like, is there a signal when the gravity wave comes in parallel to the B field? So this is a symmetry question, which is most likely purely academic until we have detected something. I think up to order 1 factors, the electric resonances, I think there's agreement in the sensitivity estimates. But then for the mechanical signals, I think it has been realized in Magro that they are much larger if you take into account the motion in this proper detector frame. So we want to make sure that we don't underestimate the sensitivity of something like abracadabra. This is kind of the goal. So if anything, we want to get more signal.
Can you quantify this somehow to get a feeling? Are we discussing about a factor of 2, 10, or 20%?
We might be discussing about something like wavelength times the typical length scale of the experiment divided by the speed of sound but this is squared, I think. Is this? Did I do it correctly? But yes.
The sound of velocity here is not in C now. It's in actual.
You have dimensions there, yeah.
Let's think. Is this the right, wrong, the correct way around? So if
no, wait.
Is this I mean, this is a result from the Mago.
For Mago, it's a speed of sound squared enhancement of the electric field that you would observe, right?
Okay.
So in the proper detector frame, you can see that it's omega L, but it's effective L. It's not necessarily physical L. So in the case of an electromagnetic resonance, it really is physical L because of the speed of light being 1. But the effective L for a mechanical object is enhanced by the speed of sound, right? So it's the effective length is length of the object physically divided by speed of sound. So what you wrote was correct.
Yeah.
Okay. But the enhancement might be, and speed of sound in a metal is something like 10 to the minus 5. So the enhancement could be 10 to the 10 if I'm close to these resonances. So there it might really matter.
Yes.
Oh, I raised some doubt on the equation in the Berlin ETAL, which appears very often in these conferences. I better clarify what's going on there. And what I found as in my view, mistake is that although in the environment of gravitational waves, we are in a curved space-time, so the definition of the electric and the magnetic field should be based on that curved space-time. But if you go their paper, they adopt special relativistic definition. Just that. I mean, there is no, mysterious things going on. It's just a simple mistake in that way. And the consequence is a dramatic violation of the correspondence between gravitational wave and action. Gravitational wave has much richer physical content by changing the homogeneous part of the Maxwell equation as well. And maybe it has a more richer experimental possibilities opened up. So we better clarify. And what I'm raising is not very mysterious things.
Yes.
And
so I mean, But do you agree that the observed magnetic field or electric field is given by such a contraction with a tetrad?
Oh yeah.
This you agree?
Using the tetrad, the things are more easily resolved. In tetrad, you can use special relativist definition or even. But what you found in the Berlin's paper is not in that tetrad yet.
But I think a question here is not whether, having two different formulations doesn't mean that one of them is wrong with respect to the other. One has to work out the consequences to the end and see whether the answer is the same or not, I think. I actually, I told you many times, I think if you work out the consequences of your formulation till the end to get an answer, if you put the same assumptions, you will get the same answer.
That's your duty to show that although I claim that your formulation is not
claiming that
correct,
we are wrong.
If it is coincide, you should show. And what I'm saying is that gravity naturally excites the homogeneous part as well as inhomogeneous part of the Maxwell.
Yeah, but that statement is a bit obvious. That's not the point. The point is that
gravity cannot be handled using using currents.
Yeah, that's true. But the point is that if you drop the charges, this is a well-known fact. If you drop the charges and the currents in the Maxwell's equations, it is true that you can rotate the electric and the magnetic field and then redefine them. So this is what you really have to do is to calculate an effect. This is not.
Perhaps we can continue our discussion, but I believe I made my point clear.
Okay, so I just want to clarify. So I think he correctly pointed out what you mentioned. So you agree with his formulation? Then I just want to clarify. So you are here and he presented and talked about some indices up and down. I just want to.
So just to clarify, I think I agree. Actually, what you are doing makes total sense to me.
And I wonder he agrees with him.
I have to see his paper, and you see, just his function, one cannot tell whether that's correct or not.
Fernando.
No, I mean, okay.
I mean, well, I also have to see your paper, but I think at the end of the day, so it's not only the Maxwell's equations, it's also the Maxwell's equations plus the boundary conditions that matters. And I think what you are doing goes in that spirit. So in your approach, the boundary conditions, so the things that are sourcing the external fields never show up, and this is the problematic part.
So one last point I want to bring back to is Juan's point. So when you compare the preheating gravitational wave spectrum with the heating, apart from the two tails, the infrared and the UV, in between you also have some dips, right? For the preheating case coming from the turbulence and some scales.
Depends on the number of fields. If you have a single field just decaying to its own fluctuations, there's just one bump.
But I guess in the reheating case, you have at least two fields, right? Because if you just have one field, still a lot of energy density is left in that field, so you cannot really reheat the universe. That component will still. So you need at least two fields to transfer the energy successfully, and then you will see that small bump in between.
There might be two, but one could be subdominant, and then you only see just one.
No, but is it possible that you have one field and then you transfer but because
you have more than one field, but just one bump? Because the other one is subdominant.
I see. I mean, subdominant in the sense that the spectral. I mean, I see. Okay, I see. Okay, so yes, please. Sorry, Mike, please.
I don't know much about this, but I'll just ask this question. So, you have this. You have these vibrational effects and resonances, but couldn't some cases one part of a resonance cancel out the other? I mean, in a resonant bar, when you have different modes, some are not sensitive to gravity waves. So, is that relevant or not?
So between the electromagnetic and the mechanical, you can have no cancellation because the scale is completely different, right? One is speed of light, the other one is speed of sound, right? Also, as we were seeing in the plots, right? Completely different scale. Now, among either one group or the other, yes, you have cancellations, right? And this is why kind of you really have to, like as also Camilla was explaining, you really have to do the full calculation. You can do kind of a parametric estimation. It could be that your leading order term cancels because your detector is very symmetric, your gravitational wave is coming from a certain direction, right? But this is taken into account in the calculations.
That'd be very hard over the broadband because in between resonances, what's going on, I'm not sure, but they're a combination of modes, Sometimes you can't have, it's hard, like I know in axions, you can't use the same equations for broadband reactive detectors than you can with ones that suck power out, for example.
I think the question here is simpler, right? Because it's simply the question of you compute a coupling between the gravitational wave and a given mode, right? And that can vanish. And then, of course, in a real setup, you have to integrate over all modes and over all incoming gravitational waves.
Okay, so maybe one last question and then we have to stop.
Yeah, I think a question for Valerie for what you just said. So I guess in terms of overlap between the gravitational wave mode and the resonance shape of the resonance of the detector, there's another component in there which is the overlap integral with the readout. So is that also taken into account? And I guess your pickup loop has some readout overlap integral, so you have to do 3 overlaps or whatever.
Yeah, it's like, for example, in the case of abracadabra, it's a 5-dimensional integral that we end up doing. So the volume and then the area of the pickup loop. And so Mook is the only person who can compute them.
Okay, so we had nice discussions and we can continue the discussion in the afternoon session or in the collaboration.